Okay, in this video I'm going to be working through most of the Unit 11 worksheet. I will not finish it in this part. I'll have a part 2 upcoming, but I'll work through the majority of this worksheet. So number 1 says to name 4 biomolecules which involve adenine besides DNA and RNA. There are many of these, ATP being one of them, NADH, NADPH, ADP, coenzyme A. There are many examples of these, and several more. But adenine is kind of like the choice organic base for energy production for whatever reason, and so it is in all sorts of different molecules. Okay, moving on to number 2. Draw the products from the complete hydrolysis of the following molecules. Remember that at esters, the molecule will be hydrolyzed in between the two O's, right there, which means water will come in and split that molecule. In this case, there are 3 carbons, 1, 2, 3, and then the carboxylic acid. And then the other part of the molecule has 3 carbons as well. So we get a carboxylic acid and an alcohol as our products. And remember, if the pH was low, or excuse me, if the pH was high, then this would be deprotonated. It would be the carboxylate ion. Depends on the pH. Alright, in the next one, this is a triglyceride. So again, the hydrolysis will occur at these points in the esters, and it literally just breaks and splits. So there's 1, 2, 3, 4, 5, 6, 7, 8 carbons on one of the molecule parts, and I believe each one is the same. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so 3 8 carbon molecules. I'll just draw this once, okay, just to illustrate. I'll draw 8 carbons, and on the 8th I will put the carboxylic acid. Like so. And then the glycerol would be the other molecule, keeping in mind that this is connected. So I need to put the H here. And then if I do this fully correctly, I'm going to have 3 waters which are involved here. I guess I didn't put that here. This would be just 1 water involved on that reaction. So 3 molecules. This comes from 1, 2, 3 of these, and they're all the same. So I can do it this way, plus the glycerol. On this one, this is actually a dipeptide. This amino acid is glycine. This amino acid is glycine. So the hydrolysis of a peptide is going to occur at the amide. And then I'm just going to draw what remains. So this NH3 plus, CH2, and CO minus. The reason why it's a minus and not a carboxylic acid in this case is because I can look here and see that the pH of the environment that this amino acid is at is a more basic pH, like 7 or above that point. Really, any pH above about 4 will be deprotonated here. So let's just assume it's a pH of 7 because this is deprotonated. So I'm going to draw the products deprotonated as well. NH3 goes here. Here's the O from the water. Here's the additional 2 H's from the water. They go on to the nitrogen. And then CH2, and then once again decarboxylate. If I draw the reactant here, it's water. Speaking of reactants above arrows, that's what's going on here. Okay, this is a reactant. I could draw it also like this, where NADPH is coming in, and if NADPH is a reactant, then NADP plus will be the product. So that means this must have gotten oxidized. Therefore, this must have gotten reduced. And if this got reduced, then the resulting molecule would be an alkane. And this is an 8-carbon alkane, and this was an 8-carbon alkene. So NADPH can come in and reduce. It basically adds these two H's to this double bond, creating CH2s here instead of CH's. So let me say that this was reduced and this was oxidized. Oh, I wrote that backwards. Oxidized, this was reduced. There we go. Alright, on the next page we have more of the same. Okay. Once again I'm going to draw an arrow, and the NADH is what results from this, because NAD plus cannot be further oxidized, so it must be getting reduced. And if NAD plus is getting reduced, this must be getting oxidized. So I need to draw an alkene somewhere. And you can draw it either here or on this bond, doesn't matter. The point is you have to take into account that carbon will only need 4 bonds. So I need to write this as CH2, then CH, then CH3. So this got oxidized and that got reduced. Same thing's going on here. NAD plus cannot be oxidized, so it must be getting reduced to NADH. And if this is getting reduced, I see there's an alcohol here, and that can be getting oxidized. You wouldn't know necessarily to oxidize the alcohol versus adding an alkene here, so if you drew it as an alkene, that's acceptable as well. But in general, if NAD plus is involved and there's an alcohol, that's what's going to be getting oxidized. And so it will be oxidized to a ketone in this case. And I'll draw the rest of the product like so. So the alcohol was oxidized to a ketone, and NAD plus was reduced to NADH. In this case, this is going to be oxidized because it cannot be further reduced, so the resulting product will be NADP plus. If the ketone is involved and this is getting oxidized, then the ketone must be getting reduced. So it's kind of the reverse of this reaction up here. It will be getting reduced to an alcohol. And the remainder of the molecule there. So the ketone gets reduced to an alcohol, NADPH gets oxidized to NADP plus. Alright, number 4, it says write in a few sentences what is happening below, include all reactants for each step, and products, if possible, indicate where there is oxidation reduction occurring. Okay, so I'm not going to write the sentences out, I'm just going to explain it. But I will write out the reactants and the products. So on this, if I'm taking this first step here, pyruvate to acetaldehyde, the reactants are going to be just pyruvate. I don't see anything else that's reacting here. There's nothing on this side of the arrow. So the reactants are pyruvate. The products are CO2. That's coming off of this reaction. That's a product. And acetaldehyde. On this step, the reactants are NADH, and you can put a little slash there, H+, and acetaldehyde. The products are NAD plus and ethanol. You can see that here. NADH and this are reactants. NAD plus and ethanol are products. Okay, so what is going on here In words, you could write that pyruvate is being converted to acetaldehyde, and in the process, CO2 is being released. Then, acetaldehyde is getting reduced to ethanol. The aldehyde is going to an alcohol, so that's a reduction. Oxygen bonds are being lost, hydrogen bonds are being gained, and NADH is getting oxidized to NAD+. So that's kind of how you would explain this process in words. On the next one, we can do a similar thing. Let's start with step 6 down here. In step 6, succinate is a reactant. So I'll kind of write step 6 and reactant, succinate, and then FAD is another reactant. FAD and succinate. Products, FADH2 and fumarate. Okay, that's step 6. I'm going to write the same for step 7. Fumarate is our reactant for step 7, along with water. And the product here is malate. Okay, so just beginning with step 6 here. Step 6, succinate is being oxidized to fumarate. I know that because hydrogens are being lost because there's an alkene being produced. At the same time, FAD is being reduced to FADH2. In the next reaction, there's neither oxidation nor reduction occurring. Okay, because you can see here that it looks like, oh, there's a reduction because this is losing the alkene, but it's also gaining oxygens. So it's neither oxidation nor reduction because two things are happening at the same time to the same molecule. All right, and finally number 5. I'll do number 5 and then I'll have to stop for now. Follow one molecule of glucose through glycolysis. Identify all the steps where ATP or NADH are involved. Indicate whether ATP or NADH is produced or consumed in those steps and how many are involved. And I am unprepared, so I'll be right back with my reference sheet. Okay. So, if we look at this is a lot to look at, but let's just start over here on the left. Okay, this is step 1 of glycolysis. So step 1 of glycolysis, we can see that ATP is being used. We know it's being used because it's a reactant. ADP is the product after ATP is used. So in step 1, ATP is used. We can write step 1, ATP consumed. And the question would be, how many is consumed? Well, just 1 ATP is consumed in step 1. Moving on to step 2, I don't see any ATP or NADH involved. Step 3, ATP is consumed again. Okay, so step 3, 1 ATP consumed. Alright, moving on to step 4. This is where the splitting occurs. Okay, so fructose 1,6-bisphosphate is split into 2 molecules, dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. Dihydroxyacetone phosphate is subsequently converted into glyceraldehyde 3-phosphate. So now, at the end of step 5, there are 2 molecules of glyceraldehyde 3-phosphate. Okay? In step 5, NAD is being converted into NADH. So there's a reduction of NAD to NADH. So step 6. Step 6, NADH produced. Question is how many? Well, we have 2 molecules of glyceraldehyde 3-phosphate, and we're expected to follow 1 molecule of glucose through glycolysis. So there are 2 NADHs produced for every 1 molecule of glucose. Moving on to step 7, ATP is produced. Step 7. ADP gets converted to ATP. So step 7, 2 ATP produced. I guess I could have put that over here. 2 ATP produced. Step 7. And step 8, nothing happens there with NADH or ATP. Step 9, nothing happens with NADH or ATP. But step 10, 2 ATP are produced again. Because again, this happens twice for every glucose. So step 7, step 10, 2 ATP produced. So we can say that in the process of glycolysis, just looking at glycolysis, 2 ATPs are consumed, 4 are produced, yielding 2 net ATPs and 2 NADHs are produced. Okay? Alright, well I hope that was helpful. I'll post a part 2 to this worksheet and do the rest of the questions that have to do with fatty acids and the citric acid cycle.